So that brings us to the final presentation of today's session, which is also the final presentation of the FM conference, this year's. After which we will have still the closing of the conference. So please do stay with us. So the last presentation is on model check and collision avoidance of nonlinear autonomous vehicle models, and Rong Gu will be presenting it. This is again a long paper, so you have about 15 minutes for your presentation, and then we have about 5 minutes for questions. Okay, Rong, please go ahead.
Oh, you hear me?
I hear you, and I can see your slides.
Nice. Okay, thanks, Maurice, for the introduction, and hello everyone. My name is Rong Gu. I'm a PhD student from Mälardalen University in Sweden, and this is the joint work with my supervisors, Christian Siciliano, Edward Yinon, and Christian Lundqvist. Before I go to the presentation, I'd like you to know that I have uploaded the complete version of the presentation in YouTube, which has all the technical details. So you can just search FM'21 and my name Rong Gu on YouTube, or simply scan this QR code to get to it. So I will keep the presentation relatively simple. So ever since the first autonomous driving car was tested on road, there are several accidents every year involving this kind of systems. So what makes them so difficult to guarantee the safety? We'll be looking at the challenges for realizing the reach and void requirement of this kind of systems. The reach and void requirement needs the vehicle to travel safely from the initial go area, the initial area to the goal area. And as you can see in the picture, if the vehicle can follow the reference path, which is the green line here, strictly, it can be guaranteed to be safe. But the truth is, the real trajectory, which is the dotted right line here, it has some inevitable deviation from the reference path. So collision can happen, and also the real trajectory can end up to a position that is out of the goal area. And also in some other situations, there are some dynamic obstacles whose trajectory are overlapping with the trajectory of the autonomous vehicles. So collision can also happen in these situations. And what about the traditional methods like testing and simulation? Well, accidents can actually happen at any moment, any place, from any angle in the environment. So there's no amount of testing and simulation that is able to enumerate all the scenarios. So what we want to do is to use 4 methods to verify the reach and void requirement. And we'll use model checking, which traverses the state space of the model and checks if some propositions or temporal logic properties can be satisfied by the states. Here I give you an example of a hybrid automaton of a car. It has 2 discrete locations, stop and move. It has 2 continuous variables, speed and position. And the derivative of position is another variable, speed. So this makes the model nonlinear. And model checking nonlinear hybrid models is undecidable. So what do we do? We want to transform the model that is undecidable by model checking to a form of another model that is decidable by model checking. This is what we want to do. And briefly speaking, we propose 2 theorems which transform the continuous trajectory to which contains the tracking arrows to a piecewise continuous trajectory, which is the reference trajectory. And then we further transform the model to a discrete time trajectory. And also we prove via these 2 theorems that the reach and void requirement or property of the continuous trajectory can be preserved by the discrete time trajectory. And what we do in Theorem 1 is that we use previous work published in CAF 2020. It has a concept called Lyapunov function, but I don't have time to explain it. All you need to know here is that if the tracking arrows have a Lyapunov function, then they are bounded within a certain region, like the yellow area here, centered by the reference trajectory. So it means that the real trajectory can never go outside the safe region here. And in our paper, we also include dynamic obstacles. So now we can actually get rid of the real trajectory, but only look at the reference trajectories. So if the safe region never overlaps with the static obstacles and the safe region of the dynamic obstacles, then the real trajectory is guaranteed to be safe. And similarly, they can reach the goal area. Okay, even though the problem is simplified, still model checking the reference trajectory is undecidable. So we need to further transform the model to a discrete time trajectory here. What we prove in Theorem 2 is that if the sampling period on the reference trajectory, of course, if the period epsilon is less or equal to s divided by the mode of v, and s here is the sum of the vehicle's tracking error boundary and the smallest tracking error boundary of the dynamic obstacles. And v is the maximum velocity of the dynamic obstacles. So if epsilon can satisfy this condition, then Theorem 2 holds. It says that if the discrete time trajectory can satisfy the rich and void requirement, then the reference trajectory must also able to satisfy the rich and void requirement. Okay, now I very briefly introduced the theorems. So if you want details, just check our paper or the complete version of the presentation. So now we transform the model from undecidable problem to the decidable problem. And now I'm going to introduce the model. We use time automata in UPO, UTA, to build the model of the discrete time trajectory. And this picture shows the UTA templates of the autonomous vehicles. Picture A is the vehicle controller, and picture B is the parameter UTA template. So if we instantiate the parameter UTA template, we can get the models that change the parameters of the vehicle, like their positions, their velocities, etc. And what we do in this model is that we, at the end of every PM time unit here, which is the sampling period, the controller UTA invoke the parameter models to change the values of the parameters. And then it makes a decision based on different scenarios. Maybe the vehicle needs to turn or go strictly or avoid a dynamic obstacle by doing this function avoid. I will go into this function later. And these two pictures show the UTA templates of the dynamic obstacles. Picture 1 is called obstacle initializer, which non-deterministically chooses the initial values of the parameters of the obstacle, like their position, speeds. And picture B models the movement of the obstacles. So basically it changes the position, speeds, and heightings of the obstacle periodically, and also non-deterministically chooses the heightings and accelerations periodically. So the vehicle can have the chance to change their direction and acceleration after a certain period. So what we want to achieve by using these models is to create an environment where the obstacles, the dynamic obstacles, can appear at any positions at any moment and travel at any speed to or from any angle within their capabilities. So if the vehicle model can actually satisfy the rich and void requirement in this kind of environment, then we say, okay, it can be safe and be reaching the destination under any circumstances. Now, after the model, we can have a look at the concrete steps of our method. So initially, we want to have the nonlinear vehicle models, of course. Then based on the models, we calculate the tracking error boundaries, and we need to slightly change the templates like the sampling period. And we need to configure the parameters like the map size, the maximum vehicle speeds, etc. And then we use all the information to instantiate the UTA templates to get the models, and we check it in a tool called UPO-Stratego. Now, people who are familiar with UPO-Stratego may get a little bit confused because this is the tool for synthesizing controllers, but it's also integrates the model checker UPO, statistic model checking UPO SMC, and the UPO TIGA. So in this paper, we only use its function of model checking because the latest version of UPO-Stratego supports calling external functions, external libraries, like here. So we can actually implement the collision avoidance function as an external library, which can be .dll in Windows or .so in Linux, and we link it to the model checker. What we do here is that we, so if the controller UTA transfer via this edge and doing this function avoid, the model checker invokes or calls external library and also pass the information of the vehicle, the obstacle, the map to the external library to do the calculation. And then the library returns the target position or speeds for the vehicle to be able to avoid the dynamic obstacle in the next sampling period. So this is what we do. And if the verification pass, then we know, okay, the reach and avoid requirement can be satisfied under any circumstances. But if the verification fails, we can also get the counter examples to show to improve the collision avoidance function. And what we do in the paper is that we conducted an experiment on a collision avoidance algorithm based on dipole flow fields. It is developed by our colleagues from Magdalen University. What the algorithm does is that it generates two kinds of fields. The static flow fields in picture A generate the attractive force along the reference trajectory, which can draw the vehicle to the reference path and finally to the destination. It also generates the repulsive force surrounding the static obstacles, so they can be pushed away from the obstacles. And when the vehicle encounters some moving or dynamic obstacles, the algorithm treats them as two dynamic dipole fields. So you can imagine them as two magnets with opposite dipoles. So the closer they get to each other, the further they or the stronger the repulsive force can be, which push them away from each other. So now the problem is if the algorithm can be working correctly in the model or in the system. So we programmed the algorithm into an external library and ran the model, verify the model, and we got two problematic scenarios. In picture one, so the red dots are the positions of the dynamic obstacles in different time points, and blue dots are the autonomous vehicles. They are the positions of autonomous vehicle. So in this scenario, the vehicle it's drawn to the dynamic obstacle instead of being pushed away. This is weird. And in the second scenario, the vehicle travels towards the dynamic obstacle. So the attractive force attracted to the goal station, to the destination. But when they get close to each other, the repulsive force just push them away. And this just happens forever. So we call it a levelock scenario. So based on these two counter examples, we improved the algorithm and we did the verification again. And what we found is that in the scenarios with only one dynamic obstacle, the algorithm can enable the vehicles to avoid the obstacles and also reach the destination. But if the environment has two dynamic obstacles, the collision is inevitable. But since we don't stop the vehicle, even though a collision happens, so the attractive force can still draw the vehicle to the destination eventually. And you can see the verification time is seconds or minutes, so it's reasonable. Okay, in conclusion, we proposed two supported exhaustive model checking for the reach and avoid function of hybrid autonomous vehicles. And we proposed Theorem 1 and Theorem 2, which transform the undecidable reach and avoid verification of nonlinear vehicle models into a decidable approximation or a conservative transformation. And in our experiments, we show that our approach is able to find or demonstrate the absence of problematic scenarios or bugs in the model and system. So for future work, we want to use statistical model checking on the cases where the distance between the dynamic obstacle and the vehicle are close, but collision doesn't necessarily happen. And also we want to explore more cases with more complex kinematic scenarios like robotic arms. Okay, that's all for the presentation. And again, the complete version is on YouTube, so please check it if you are interested in the details. That's it. Thank you.
Thank you, Rong, for this nice presentation. So if anyone has a question, feel free to raise your hand or write it in the chat. Let me start with a question. So you presented this nice slide around 25, 26 somewhere on the process that you described, right? Yeah, this one exactly. So where's the manual in intervention exactly?
Yeah, the manual intervention is in step 1 because this is based on the previous work that I mentioned, published in CAF 2020. And also you need to manually configure the parameters and also slightly change the templates. That's it.
Yes. Okay. So changing these templates, would I be able to do this, or do you really need an expert like yourself?
I don't think so, because you see, I didn't have time to introduce this. We have these parameters on top of the models. They are very, we have comments. Okay.
We can hear.
Yeah, what I want to say that we don't directly check or verify the hybrid models. We transform it to a discrete time model by using these 2 theorems. So we can check the theorems in the paper.
Okay.
Is that okay? Yeah.
I'm waiting for David to react, but I think it's okay. So well, so it's we have just yeah. So he's satisfied with the answer. I see no other questions. So I think we can thank Rong once again for this nice presentation and all the presenters in this last session of the conference. So